Hello everyone, today we're going to be going over part A of the June 2022 Physics Regents exam. We're going to be starting off with question 1, which asks us to identify two scalar quantities. Right, so in physics you have two different quantities. You have vector quantities and you have scalar quantities, right? Right, so both vector and scalar quantities have units. Right, they have magnitude. Right, and all that magnitude means is that they have a number associated with them, right? So a scalar quantity like 10 grams, right? That 10 is the magnitude. The same way that a vector quantity like 10 meters per second east has that 10 or has a number associated with it, right? And pretty much the only difference between a vector and a scalar quantity is that with a vector there's always direction associated with it, and with the scalar quantity there's never going to be direction associated with it, right? So looking at these choices, we can eliminate choice 1 and 1, 2, and 3, right? Because number 1, velocity has distance. Velocity has to be a vector, right? For example, my velocity can be 25 meters per second, right? And because it's velocity, I have to state a direction, right? So 25 meters per second north, right? Or east or west, right? Same thing goes for impulse. So same thing goes for impulse, right? Because you need to apply the impulse in a specific direction in order for that scenario, for that actually to be able to apply to it, right? And force and acceleration are both need direction associated with it, right? Look at force right here, 10 newtons. That's the measurement of a force, right? And that force is being pointed in this direction, right? That value has direction associated with it. When we're talking about acceleration, look at problem number 2. It says he's accelerating uniformly at a rate of 3 meters per second east, right? Acceleration has a direction, right? And then for velocity, he's saying that has a final velocity of 21 meters per second east, right? So because all of those values have direction associated with them, they cannot be scalar. That leaves us with answer choice 4 as our answer. Usually scalar values are units of measurement, and time and energy are definitely units of measurement, right? Time, there can't be any direction with time, right? 5 seconds is 5 seconds, right? You can't have 5 seconds north, doesn't make sense. Same thing goes for energy, like 5 joules is always going to be 5 joules, right? 5 joules north doesn't make sense, 5 joules south doesn't make sense. That's all, right? So just know that the distinction is direction. Number 2 says a motorcyclist initially traveling at 15 meters per second, right? So they give us VI, V initial. I'm just going to write that down, keep note. 15 meters per second accelerates uniformly at a rate of 3 meters per second, right? They give me acceleration. And he accelerates to a velocity of 21 meters per second, right? So velocity final is 21 meters per second. And they're asking us how far does a motorcyclist travel, right? So they're asking us for D. Obviously, this is going to be a calculation problem, right? So I wrote down everything they gave us, right? So they gave us VI, A, VF, and D. Now, if this was the real test, I'm going to go to my reference sheet. I'm going to zoom in a bit, and I'm going to look for a formula that works with velocity initial, velocity final, acceleration, and distance. And I'm going to see that it's this is the formula that incorporates all of those units, right? I can't use this one because it doesn't talk about v initial, right? Or sorry, rather it doesn't talk about distance at all, right? And I can't use this one because it doesn't incorporate velocity final, right? So in order to find my formula, I'm just gonna have to write everything that they give me and everything that they're asking me, and I'm gonna match that with whatever formula is here, right? So now that I know my formula, I'm gonna just plug in all my values and then solve algebraically, right? So here I'm going to zoom in and I'm going to write VF squared is equal to VI squared, right? Plus 2AD, right? We know that our final velocity is 21 meters per second, so I'm going to have 21 meters per second squared is equal to our initial velocity, which was 15 meters per second squared, plus 2 times our acceleration, which is 3 meters per second squared, times D, which is the thing that we're solving, right? So in order to solve this, literally just solve it any way you would for like a basic algebra problem, right? Subtract 15 on both sides. So now you're left with 21 meters per second squared minus 15 meters per second squared is equal to 6 meters per second squared times d, right? And in order to solve for d, just divide this entire both sections by 6 meters per second squared, right? And you're going to be left with 36 meters as your solution, right? D is equal to 36 meters, right? So moving on to number 4, number 3, it says a battery-powered electric motor, right? That's important. It's an electric motor, is used to cause the wheels of a toy car to rotate. In this motor, there's a conversion of what to what, right? So a battery stores electrical energy, right? And it's only going to store a source of an electrical energy, right? And if this battery is powering an electric motor, right, that motor is using electrical energy, right? So we're going to start off with electrical energy that we're getting from this battery that stores electrical energy, right? So we can automatically eliminate choices 1 and 3 because that just simply doesn't make sense, right? Where are we getting mechanical energy from? Where are we getting thermal energy from? We're getting all of our energy from the battery, right? And once we get that electrical energy from our battery, our electric motor, right, is then using this electrical energy to make the wheel of a car rotate, right? So when I think of rotation, right, something's moving, right? The wheel is moving, right? It's being spun. And whenever I think of movement, I'm going to think of mechanics or expenditure of mechanical energy, right? Rotation is movement, and anything that requires movement is mechanical. Right, a cool way to remember this is that M and M. The M in movement stands for mechanical, right? So what's really happening here is that we're taking all that electrical energy in the battery, right? And the electrical motor is converting it or applying it to rotate something. In other words, it's taking that electrical energy and it's turning it into mechanical energy, or it's turning it into movement, right? So that's choice number 4, right? Chemical energy wouldn't make sense here because of rotation is mechanical. Moving on to number 4, it says a projectile is launched horizontally from a height of 65 meters. Right, so I'm going to go ahead and write that, 65 meters, and here's my object. Right, with an initial horizontal velocity or horizontal speed of 35 meters per second, right? Notice how they say speed and not velocity. If they said speed, that means they don't need to give you a unit, right? Oh, sorry, they don't need to give you direction, right? So if this is launched at 35 meters per second, and this is my velocity horizontal, they're asking us what's the projectile's horizontal speed after it has fallen 25 meters, and it's saying neglect friction, which is really important. Well, when there's no friction involved, and whenever you have projectile motion, right, your velocity horizontal velocity, right, is always going to stay the same. It's always going to stay constant, right? It's never going to change because there's nothing slowing it down. There's no air friction slowing it down. If I launch that object 35 meters, right, there's not going to be any air to really stop it or slow it down. And what I'm trying to get at here is that your horizontal velocity is always going to be constant, right? This is probably one of the biggest things that they teach you in Regents physics, is that horizontal velocity stays the same, right? Vx or v horizontal initial is the same thing as v horizontal final. Right, and this only works for projectile motion, but pretty much that's the rule, right? It stays the same. If our initial speed was 35 meters per second, our final is going to be 35 as well, right? Number 5 says the diagram below represents two forces, F1 and F2, acting concurrently on a block sliding on a frictionless surface, right? Which statement describes the motion of the block, right? So here I have our velocity, right? Notice how there's direction associated with it, right? That makes it a vector quality, and this velocity is going to the right. Right, so we know that we're moving to the right. Perfect. Right? So what I now know or what I now have to look at, now that I know which way it's moving, is I need to look at what forces are acting on it. Right, over here I can see that there's a force of 10 newtons acting toward the left, and there's a force of 10 newtons acting on the right. Right, so they're acting in opposite directions, right? And let's just say that anything facing to the left, let's just draw a little compass, right? So here's going to be nope, that's flipped. So here's going to be north, east, south, west, right? And let's think of this as like a coordinate plane, right? Anything going east or anything going right is going to be positive, right? or it's gonna be on a positive x-axis, and anything on the left, going left or going west, is going to be negative, right? So let's just think of this 10 newtons that's going left as negative 10 newtons, right? And let's think of this 10 newtons going right as positive 10 newtons. And when I add these two up, right, 10 newtons plus negative 10 newtons, right, these are going to add to 0 newtons. Which, what I'm trying to get at here is that even though there are forces acting on this block, they cancel each other out, right? And because they cancel each other out, there's really nothing acting on this block. It's going to continue moving toward the right as if nothing is happening, right? If this 10 newtons wasn't here, right, then it would be accelerating to the right, right? Because that force would be pulling it. But because you're pulling the force in both directions at the same with the same amount of force, or with the same value of force, right, nothing is going to change. It's going to continue moving right at a constant speed, right? Which is choice number 3. Whenever you have two forces, two or four forces which all balance each other out, that object is in equilibrium, right? There's an equal amount of forces on both sides, they cancel each other out, and you're just going to continue moving as is, or you're not going to move at all, right? In this case, it was moving here, so it's going to continue moving unimpeded because these two cancel out. That's all. Right, so number 6 says the magnitude of an unbalanced force applied to a 4 kilogram crate is 10 newtons. If the magnitude of this applied unbalanced force is doubled, then the inertia of the crate is what, right? So here we have a crate. It's 4 kilograms, and it's being pulled with a 10 newton force is being applied to it, right? And it's asking us about the inertia. Well, an inertia kind of relates to the first rule of physics, or Newton's first rule, where it says that an object in motion will want to stay in motion, right? And inertia is really reliant on the mass of the object, right? And it's only reliant on the mass of the object, right? What I mean by this is if you have a very heavy object staying, which is in motion, it's going to want to stay further in motion, right? Think about you in a car or in a moving vehicle, right? And then the driver brakes, right? They press the brake, and notice how your head always like jerks forward or moves forward. That's because your body is an object that wants to stay in motion, right? Your head is going to want to continue moving forward as it was all that time ago, right? But really, there's a force acting there. So while you are slowing down, your body still wants to go forward. That's why you move forward, right? Probably the heavier you are, the more like apparent that that force is going to be, or the heavier you're gonna slam forward in that car. That's because inertia is reliant on mass, right? The heavier an object is, the more inertia that object will have, right? And here we're only changing the unbalanced force, right? Force has absolutely nothing to do with inertia, right? So it's going to remain unchanged, right? The only thing you can do to change inertia is change your mass. If they wanted to add 4 kilograms to this cart, right, then that would probably double our inertia, the inertia of the cart. But since the mass is staying the same, the inertia is staying the same, right? Number 7 says a 60 kilogram man is pushing a 30 kilogram lawnmower. Compared to the magnitude of the force exerted on the lawnmower by the man, so this is saying compared to the force that the man is putting on the lawnmower, the magnitude of the force exerted on the man by the lawnmower, or in other words, the force that the lawnmower is applying back to the man is what? Well, you should be thinking of, I think, Newton's third law, which is every action has an equal and opposite reaction. And what this means is that when this man is pushing his little lawnmower, I guess this looks more like a tractor, but when he's pushing this lawnmower, he's applying a force onto that, right? And let's just say that's 5 newtons, right? It's a 5 newton force, and he's applying it onto the handle of this, right? So there's a 5 newton force being applied to this handle, right? So that's his action. His action is that 5 Newton push, right? And it's saying that every action has an equal, right, an opposite reaction, right? So if he's pushing this, the equal and opposite reaction is that this handle is going to push back 5 newtons, right? 5 is equal to 5, so that's the equal part. And the opposite is just the direction of that. The direction that is pushing is just going to be flipped, right? So if he pushes 5 newtons, the cart is going to push by the same value, 5 newtons, just in the opposite direction back. And this goes for anything. If let's say I punch like a wall, right? Pow. Or fine, bow. You know, because I'm super strong. I punch it with like 1,000 newtons. You know, that wall is going to hit me back at 1,000 newtons, right? Because every action, me punching the wall, has an equal and opposite reaction, which is 1,000 newtons, just facing the opposite way. This is why whenever you hit something, whenever you hit a table really hard, your hand's gonna hurt because the table is hitting you back with the same force that you hit the table, right? So what I'm trying to get at is that the force that the man exerts onto the lawn, or the force that he pushes it with, the lawnmower is going to push him back with the same force, right? The same force, because every action has an equal and opposite reaction. So moving on to number 8, it says the diagram below represents a roller coaster car traveling counterclockwise in a vertical circle. When the car is in the position below, what are the directions of the centripetal force acting on the car and the velocity of a car? Well, centripetal force, or FC, is always going to be pointed to the center of the circular or of the round path, right? So this is focused, or this is directed towards center, right? So the FC is going to be directed to the center. In this case, the center is to the right, so the FC is going to be directed to the right. So let's look at a choice that says that. We could eliminate choice number 2 and 4, right? Because both of them say that it's directed not to the right. Right? So now we're just going to have to deal with the velocity, right? And the velocity is always going to be perpendicular to the centripetal force, right? So that means that in this case, there's two things, right? The velocity is always going to be tangential to the path, the circular path, which means that it's going to touch the circular path at one specific point. That's one. And 2, the velocity is always going to be perpendicular, right? It's going to come in at a right angle to the centripetal force, right? So if the centripetal force is pointed this way, right, the velocity is going to be at a right angle or perpendicular to it, right? So automatically I can eliminate choice number 3, which says that both of them are directed to the right, because the velocity is going to be either directed up or down, right? Now we know that the velocity is going to be directed down because look at the direction of the car, right? The car is going down, right? It's going to counterclockwise, right? So if we just trace this downwards at this point, right? If we literally just trace it and then draw a straight line, it's going to go downwards, right? So that's all you have to do here, right? Just follow this line until you reach the car and then just go in a straight line. And look, you have a tangent line, right? It touches it at one point and it's facing downward, right? And it's also at a perpendicular or 90-degree angle facing downwards, right? So choice number 1 is the only one that says that. Number 9 says an electric motor with a power rating of 6.4 times 10 to the power 4 watts, right? So I'm given power, P, and that's 6.48 times 10 to the 4 watts, is used to raise an elevator weighing 2.8 times 10 to the 4 newtons, right? Well, newtons, anytime you see a newton, that's dealing with force. So I'm just going to write down that I have force, or F, right? And it's at a constant speed. And it's asking us what is the total time required for the motor to raise the elevator a vertical distance of 20 meters, right? And I'm also given D, 20 meters. And I'm trying to find S. Right? So this is not a conceptual problem. This is a calculation problem, so I just started writing down everything that's given to me and everything that they're asking for me, right? So I'm given power, I'm given force, I'm given distance. Sorry, that's supposed to be a lowercase d. And they're asking me for time, right? So I'm gonna go ahead. I'm gonna look at my reference sheet, and I'm gonna see which formula has P, F, D, T, right? If I look all the way down here, right, it's the formula for power. So power, which was given to me, and it's saying that here it's equal to Fd over T, right? So I have Pfdt. I have power, I have force, I have distance, and I have time. That's all that they were asking for me, right? So I'm going to use this formula, right? So I'm going to zoom in so that I have space. I'm going to write power is equal to force times distance over time, right? So here it said that we had a power rating. Whenever you see power rating, same thing as saying the power of this is equal to this, right? So because the power was 6.48 times 10 to the 4 watts, this is going to be equal to our force, right? And our force is 2.8 times 10 to the power of 4 newtons, right? Because force is always in newtons. And it's being applied over a distance of 20 meters, right? It tells us if it's moving a vertical distance of 20 meters, that means our d is 20 meters, right? And this is all going to be divided by t. In order to solve this, I'm going to multiply both sides by t, so I'm going to be left with 6.48 times 10 to the power of 4 watts times t, and that's going to equal 2.8 times 10 to the power of 4 newtons times 20 meters. And then in order to isolate t, I'm going to divide everything by 6.48 times 10 to the 4 watts. And I'm going to be left with t, and if you put this into your calculator, and if you look at what this is actually equal to 3, which is 8.64 seconds, right? Perfect. So moving on to number 10, it says that a person standing on a sidewalk hears the siren of an ambulance as it approaches, passes, and goes away from the person. Compared to the frequency of the sound emitted by the siren, the frequency of the sound observed by the person during this event is what? Well, automatically I'm thinking about the Doppler effect. Why? Because I have sound and I'm observing the frequency or the pitch of the sound as it's moving toward and away from me, right? So here, I'm just gonna show it how it is. I'm gonna draw the siren, right? So it's gonna be this little box, and then right here is gonna be a cone, and then the sound waves come out of this cone, right? So normally, and remember that this cone is moving this way. Let's just say it's moving this way. And this is attached to an ambulance, wee woo, a sick person coming through, clear the way, and then here I'm gonna be standing, right? And I'm gonna be happy that they're getting to the hospital on time, and this siren is going to be emitting these sound waves while it's moving here. So it's going to be emitting these sound waves, and it's going to be emitting them pretty frequently, right? As it should be. But as the siren moves toward the left, right, what's going to happen is the speed of the vehicle is going to end up stretching these sound waves around the back of the vehicle, right? So as much as these sound waves want to go out, and out, right, part of them is going to be stretched around the back of the vehicle, and because it's moving forward, they're going to be stretched outwards around the back, right? I don't have a camera on right now, but I'm kind of doing a motion where you you charge up a bow, or like you wind back a bow. That's pretty much what's happening to these sound waves, right? They're getting stretched out as they reach the back of that vehicle, right? So I'm left with this kind of strange shape, right? And I wanna just make quick note of two things, right? When I look here, the distance between these sound waves, right? The distance between this, or their wavelength, is pretty small, right? So I have a smaller lambda. And because there's a small distance between these waves, right, I'm hearing them at a high frequency, right? They're coming to me quickly, right? So I have a high frequency, and I have a high frequency, and I have a smaller lambda, or I have a small lambda, right? And because there's less distance between the sound waves, I'm hearing them at a higher frequency, or they're coming to me at a higher frequency, right? Now you're saying higher frequency compared to what? Well, compared to what I hear when the truck passes me, right? When the truck passes me, these long or stretched out sound waves are going to reach me, and guess what, right? This distance between each sound wave, right, or each is way bigger, right? So I have a larger lambda, or a larger wavelength, right? Because each one of these loops is like a peak, is a peak of the sound wave, and then the next one is the next peak, right? So the distance between two peaks or two troughs is your lambda, right? But at the same time, because they have a higher lambda, they take more time. They take more time to reach me, right? And because they're taking more time to reach me, and because they're more spread out, I'm hearing them. They're coming to me at a much lower frequency, and I'm hearing them at a lower frequency, right? So here is a lower, frequency, and frequency is this little fancy f, right? So, now that we went over the Doppler effect, this happens with almost anything that emits waves and is moving, right? Closer, as you move closer to the thing that's emitting them, you're gonna have a smaller wavelength but a higher frequency. As you're moving away, you're gonna have a lower frequency but a higher wavelength, and the speed of the waves are always gonna stay the same, right? But here we're talking about sound, right? And if my frequency is higher at first, right, I'm gonna hear. Frequency is the pitch is determined by frequency, right? And if my frequency is higher, I'm going to hear it at a higher pitch, right? And if my frequency is lower after, then I'm going to hear it at a lower pitch, right? That's why you have this new, right? The beginning of that is going to be really high pitched, and then the last part of that is going to be very low pitched, right? And this diagram shows you why. So moving on to number 11, it says, which particles exhibit properties of waves in some experiments? That's going to be both photons and electrons. Photons is light. Literally, you have light waves. Light behaves as waves. Think back to your whole modern physics unit, right? And electrons, once again, think back to your modern physics unit. Electrons also behave in wave-like patterns, or like wave-like. They have properties that are like waves. Moving on to number 12 is the direction of a electric field at a point in space is defined as the direction of the force exerted by the field on what? This is a lot of confusing and big words. All they're asking us is if we have these two plates, right? And this plate is positively charged, this plate is negatively charged, and I want to know the direction of the electric field, right? Or let's say I didn't know that this is positive. Let's say I didn't know that it's negative, and I want to know which direction, right, this electric field is going in. Is it going up? Is it going down? What do I have to do, right? So automatically, what we do when we want to find the direction of an electric field, right, is you're going to have to emit a positive test charge, right? Or you're going to use a test charge, right? You're going to use a test charge, and a test charge is always positive, right? You can't have a negative test charge. So we're going to eliminate choice 3. And because we need a test charge, we can eliminate 1, 2, because they have nothing to do with that, right? And what a test charge does is it's just a positively charged particle, and we're going to emit it in the middle of these two plates, and wherever this particle chooses to go, that is going to be the direction of the electrostatic field, right? This is going to be the way in which it travels, right? Because remember, things the way that electricity flows is it flows from positive to negative, right? So if this positive electron is flowing downwards, that means that the positive side is flowing downwards, right? And that's how we measure the direction of the electric field, right? So number 13 says a net force of 1 Newton will do the what? Well, if you don't know what net force is, and even if you do, I advise you do this either way. I'm going to go into my reference table, and I'm going to see wherever I see net force, right, or F net. It tells us that right here. I see F net in this formula. A is equal to F net over M, and if I want to put this in terms of F net, I could always rewrite this. I can multiply both sides by M, right? That cancels out the denominator, and I'm left with AM, or acceleration times mass, is equal to my net force, right? So now that I have this formula, right, I have F net is equal to acceleration times mass. I'm just going to plug in whatever they tell me here, and I'm going to verify it, right? So if I have a net force of 1 Newton, right, my F net is going to be 1N. And it's saying that it will accelerate a 1 kilogram mass at 1 meter per second, right? So is 1 Newton of net force equal to 1 kilogram or 1 kg, which is my mass, times 1 meter per second squared, which is my acceleration, right? So is 1 equal to 1 times 1? Yes, obviously, right? And if you're worried about the units, a Newton is a kilogram times a meter per second squared, right? So because 1n is equal to 1 times 1, that's how you would solve this, right? All of these other choices, right, would give you values that simply don't make sense, right? A Newton net force, right, obviously cannot accelerate a 1 kilogram mass, right? Our mass is 1 kilogram and our acceleration is 9.81, right? Why? Because 1 Newton is not equal to 9.81 newtons, right? That simply doesn't make sense. Number 14 says the elongation of a spring will be quadrupled if the magnitude of the force elongating the spring is what? Right? So we're talking about the elongation of a spring, right? And it's saying that under what conditions would this elongation be or what under what conditions will the stretching be quadrupled? Like what will we have to do to the force stretching it if we want to actually stretch it 4 times as long as it already is, right? So I'm gonna look at my reference table for a formula that pertains to the spring force, right, and elongation. I'm gonna find F of S, or spring force of the spring, is equal to kx, right? And if I don't know what kx is, I know that k is my spring constant, and I know that my x is my change in spring length, right, or my elongation, right? And just to be extra safe, Fs is force on spring, right? So I'm going to write this down. Fs is equal to Kx. Perfect. So F of S, right, or F sub S is going to be the elongation. Is going to be the force of the elongating, or the force of the spring after I stretch it, right? Now, if my elongation, which is x, right, if my stretching of the spring is quadrupled, right, if I want my x to be multiplied by 4, if I want F of S is equal to kx times 4x, right, what am I going to have to do to this side to balance that equation out and make it equal, right? Obviously, I'm going to have to quadruple the force elongating the spring, right? Because if I multiply this force by 4 or this side by 4, I'm going to have to multiply that side by 4. So 4 F sub S, right, or 4 times the force exerted on the spring in order to stretch it out is going to equal to my spring constant, which stays the same, times 4 times the elongation, right, or the amount that I stretch it out by, right? If I multiply on 4 by one side, I have to multiply by 4 on the other side, and that's what makes this true, right? Number 15 says the vector diagram represents the path and distances run by a student in a cross-country race. The displacement of the student from start to finish is what? Well, displacement is a vector quantity, and what it does is it's the distance from start to end. And it's the distance from the start point to the end point only, right? The displacement does not care about this distance plus this plus this plus this plus this. It doesn't care about that. The only thing that displacement cares about is the distance between the start to the finish, right? So it only cares about this distance, right? So let's find that distance. If we know that from here to here is going to be 0.8 kilometers, right? And if we know from here to here is going to be 0.6 kilometers, then my distance from start to finish is going to be 0.8 km plus 0.6 km, which is 1.4 kilometers. Simple, start to finish. Next, I need to determine the direction, right? Because since it's a vector quality, displacement is a vector quantity, it has to have distance, right? So it's distance, it has to have direction, right? It's distance plus direction. And if we look here, we started up here, and then we ended down here, right? So technically we moved southwards, right? We moved downwards, or we moved 1.4 kilometers south, or southbound. That's all. Right, so moving on to number 16, it says that the diagram below shows the arrangement of 3 charged hollow metal spheres, A, B, and C. The arrows indicate the direction of the electric forces acting between the spheres. What spheres have a static charge of the same sign, right? So quick review of electrostatics. Things with the same charge, right? So plus plus and minus minus, they're going to repel. They're going to move away from each other, right? Because likes repel. When you have a positive and a negative, they're going to be attracted to one another because opposites attract. right? So they're asking which spheres have the same charge. So which spheres can both be positive, positive, or negative, negative, right? And the answer here is going to be A and C only, right? Because A and C are the only two spheres that repel one another, right? And if we just said that likes repel, right, we're going to be looking at the only two spheres that move away from each other, right? A and C are the only two that move away from each other, which means that they can be the only two that have the same charges, right? C and B can't be the answer because they're attracted to each other, meaning that they have to have opposite charges, and A and B can't be the same, can't have the same sign because they're attracted to one another. The arrows are moving to each other, they're meeting each other. So that's all. And A, B, and C doesn't make sense because if they all had the same sign, then everyone would be repelling one another, and all the arrows would look something like this. Right. So moving on to number 17, it says two small charged spheres are located distance d away from each other, and they experience an electrostatic force of attraction Fe. If the magnitude of the charge of each sphere is tripled and Fe is unchanged, what other change must have occurred, right? So we're talking about Fe here. And if you don't know what Fe is, perfect. It's given to you on this handy reference table right here. Fe is equal to the electrostatic constant, right, times Q1 and Q2, which is the charge of your two spheres, divided by d, or your distance between your two centers, or also known as r, right? So let's just go ahead and rewrite this formula right here. Fe is equal to k q1 q2 over r squared, right? And it's saying that the magnitude of the charge of each sphere is tripled, right? Magnitude means like the number, right? The value. So if we're tripling the value of each sphere, we can model the scenario as this, right? K times 3 Q1, right? Because we tripled both of them, right? Times 3 Q2 as well, right? Because we tripled both of them, over r squared. And really what we can rewrite this as is this: if we multiply, because we're multiplying every single value here together, right? And because our k stays the same, and because we increase these two are now equal to 3q, right? This entire numerator is 9 times greater, right? We're, in another sense, what we did is the same thing as multiplying this entire numerator by 9, right? So we have 9 times k q1 q2, right? We can just rewrite it as that. And the problem is asking us, what do I have to do in order to cancel out this 9 so that my Fe doesn't change? Because now the way we have it set up is that my force, my electrostatic force, is going to be 9 times greater because my numerator is 9 times greater, right? So what do I have to do to balance this out? I'm going to have to increase the distance d, or my r squared, by a factor of 3. Because think about it, right? If my Fe is equal to 9, right? I need my numerator to also equal to 9 so that we can cancel these two values out. My denominator is r squared, right? So if I increase my denominator by 3r, right? And after I go and square this, what is going to be left with 3r squared is the same thing as saying 9r, right? Or 9r squared. Even though we already squared the r, right? So what multiplying that by 3 is, or increasing it by a factor of 3, that's going to make my denominator 9 times as great. And when my denominator is 9 times as great, that's the same thing as saying multiplying by 9. Since I have a 9 in numerator, a 9 in denominator, they cancel out, and I'm left with my original formula. Fe is equal to k q1 q2 over r, or over r squared, and it's like nothing ever happened, right? Because those two 9s cancel out and my Fe doesn't change. Moving on to number 18, it says, compared to the resistance of an aluminum wire at 20 Celsius, the resistance of a tungsten wire of the same length and diameter at 20 Celsius is approximately. Well, I'm gonna have to go to electricity, and I'm gonna have to look at this formula, right? Resistance is equal to resistivity times length over cross section, or over cross-section area. Now, I'm going to write that down here, right? R is equal to PL over A, right? They're saying that it has the same length, right? So L is out of the game, and it has the same, what does it say it has that? It's the resistance of aluminum tungsten. Yeah, it has the same length and it has the same diameter, right? So if it has the same diameter, the cross-sectional area is going to be the same, right? So we're going to be pretty much left with just P, right, or just our resistivity, and that's going to be the only thing that's changing my resistance, right? So I'm going to look at my resistivity, right, in this table labeled resistivities at 20 Celsius, right? I'm going to look at that. My aluminum resistivity is 2.82, right, times 10 to the power of -8, and my tungsten resistivity, which is the other material, is 5.6 times 10 to the power of -8, right? And if I open up my calculator, I know that 5.6 is 1/2 of 2.82, right? Or in other words, 5.6 is twice as great as 2.82, right? And if my resistivity is twice as great, my resistance is also going to be twice as great, right? So my tungsten wire has a resistivity that's twice as great as the aluminum wire, which means that the resistance of the tungsten wire is going to be twice as great, right? Because if R is equal to PL over A, and neither one of these are changing except for P, and I multiply my P value, right, or my resistivity by 2, I'm also going to have to multiply my resistance by 2 in order to make that, in order for that to make sense, right? Whatever you do on one side, you have to do to the other. Number 19 says how much energy is expended when a current of 5 amperes, right? So they give me I, right, which is 5A, which is current, right? Is in a 5 ohm resistor. They give me R, which is 5 ohms, right? And they give me T, 5 seconds, right? And they're asking us how much energy is expended. So, and then we're trying to obviously solve for energy, right? So we're gonna have energy, or the same thing as saying power, right? So I'm gonna go ahead. I'm gonna go into my reference table, and I'm gonna see whichever gives us whichever formula in electricity, right? We're dealing with electricity because we have amps, right, and we have resistivity. Which one of these is gonna have current, resistivity, time, and power, right? So we know that it's going to be W, right? W is work, aka electrical energy, right? We just said that we're looking for electrical energy, right? So we're going to look at this formula right here, and which one has I, R, and T in it? Well, this one, I squared times R times T is equal to W, which is the work or electrical energy, right? So W, right, is equal to I squared times R times T, right? W is equal to 5 amps squared times resistivity, which is 5 ohms, times 5 seconds, right? That's the same thing as saying 25 times 25, which is 625 joules. That's what that's equal to. That's all. 20 says the amount of electric current through an unknown resistor may be measured by connecting which of the following, right? So we have two things that we can measure, or that we usually measure for in Regents physics in circuits, right? That first thing is potential difference. Right, which is voltage. And the way we measure that is we attach a voltmeter, right, which is this little guy, this V, and he has 2 legs that face downward, right? So in order to find potential difference across a resistor, across a circuit, right, we're going to use a voltmeter, right? Right, and this is connected in parallel. That's all you need to know for that, right? And the other main thing that we test for, or we measure in a circuit is current, right? Or electrical current. And that's the same thing, that's measured in amperes, or A, right? And the symbol for this is going to be I. And the way we do it is through an ammeter, right? Because V, voltmeter, and voltage are the same thing. Amperes and ammeter are the same thing, right? A goes with A, V goes with V. And the way that this happens is we have this guy who's an A, and he just has 2 legs or 2 arms that are just spread out, right? They don't go up, they don't go down, they're just spread out, right? And this guy is attached in series, right? So knowing all this, our answer is going to be 1. It's an ammeter in series with the resistor, right? If we want to find the current, we use an ammeter, and an ammeter is always in series. So number 21 says, which phenomenon best represents a wave spreading out behind the barrier as the wave passes by the edge of the barrier? The answer to this is obviously going to be diffraction, right? This phenomenon where it goes like this and it goes like this, that's called diffraction. Number 22 says a 1 kilometer length of copper wire A with a cross-sectional area of that amount of meters, right? So they give us A, and they give us L. It has a resistance of 0.172 ohms, right, at 20 Celsius, right, and they give us R. Another copper wire B is half as long and has twice the cross-sectional area of wire A. What is the resistance of copper wire B at 20 degrees Celsius, right? So what they give us is they give us A, L, R, and we're trying to find the what? We're trying to find the resistance of copper wire B, right? So we're trying to find R based on A, L, and technically resistivity, which is P. So if I go here, once again, I'm going to have to use this pretty annoying formula. R is equal to PL over A, right? So I'm going to write that down. R is equal to PL over A, resistivity over A, right? Now I'm just going to fill in whatever I see, right? So what did they say in terms of our... it's saying that wire B is half as long, right? Here it's saying that it's 1 kilometer or 1,000 meters long, right? So half of that, R is going to equal to resistivity of a copper wire, which they give us down right here. A copper wire is 1.72 times 10 to the power of negative 8, right? Right, that's a resistivity, right? And we just said that our length is half of 1,000 meters, right, which is 500 meters. So we're multiplying that by 500, and we're dividing this by our cross-sectional area, which is twice the cross-sectional area of wire A, right? In essence, it's 1.00 to the power of negative 4 times 2, right? So here we have 1.00 times 10 to the negative 4 meters times 2, right? And when you calculate all of this, right, when you calculate, I forgot to put units, but you should probably put units, you're going to get this value as your resistance, 0.0430 ohms. That's all. The magnitude of the electric force exerted on a small positive charge located between two oppositely charged parallel plates is what? Right, so again, they use kind of confusing language to trip you up intentionally. So I'm just going to go ahead, I'm going to draw out what they said, right? So we're looking for the magnitude of the electric force, right, between two oppositely charged parallel plates, right? So these plates are parallel, right, and they're also the same size, right, and they're oppositely charged, so one is positive and one is negative. And we're trying to find the electric force, right, or the Fe between the two, right? So the way that the electric field is, it's going downwards, obviously, because it goes from positive to negative. And now I want to know what's the deal with these arrows? Is our Fe the same throughout everywhere? Is it greater near one plate? Is it greater near the other plate? It's going to be the same everywhere between the plates, because if we look back at our Fe formula, right, the electrostatic force is equal to K Q1 Q2 over R squared, right? Because the charge of these two plates aren't changing, and because the electrostatic constant never changes, my entire numerator is the same. So the only thing that can really alter my electrostatic force is the distance between these two plates, right? So our test is our positive charge is located between the two plates, right? And since our R isn't changing, no matter where these plates are, right, because they're parallel, the distance between them is always going to be the same. Because the distance between the plates is the same, R squared is the same, so Fe really is never changing so long as you're between the plates, right? In other words, it's the same everywhere between the two plates. That's all. Now you put this charge like over here, your answer is going to change because your distance from the plates or the center of the two charges is going to be way different. But right here, we're in the middle where the distance is always the same. So our Fe is always going to be the same between them. Number 24 says an acoustic organ is an instrument with pipes. The oscillation of air molecules in the pipes of the organ produces sound waves that are what? Well, here we have the oscillation of air molecules, right? And whenever you have something oscillating, you have something that's moving back and forth, right? And an oscillation, since an oscillation is a type of movement, I'm going to think movement, mechanical. Movement, mechanics, movement, mechanical, right? So because sound waves are the oscillation of air molecules, right, it has to be a mechanical wave, right, because it has to deal with movement. And obviously sound waves, if you didn't know this, they are longitudinal, which means they look something like this. right? They go in like these pretty much these pulses, right? And each three of these is like a peak or a trough, and that's it. Right, so 25 says which list defines portions of electromagnetic spectrum in order of increasing frequency. You may be worrying, oh no, I don't know what my electromagnetic spectrum is. Guess what? It's on your reference table. If you scroll up, boom, electromagnetic spectrum, and anything to your left is going to be high frequency, low lambda. Anything to your right is going to be high lambda or high wavelength and low frequency. Right, so from here, automatically we know that gamma rays are the things with the highest frequency, right? They have the highest frequency out of anyone, 10 with 21 zeros attached to the end of it, right? So if it's in order of increasing frequency, gamma rays should actually be at the end, right? And our answer here is going to be 3, right? Because if we look at ultraviolet and infrared is going to be the smallest in terms of frequency out of any of this list, right? We go infrared, then we go visible, right? Visible has a slightly higher wavelength than a slightly higher frequency than infrared, right? And then from infrared we go into ultraviolet. UV is right here after visible light, and finally we finish off with gamma ray. So that this is increasing. This increases into this into this, and this finally into that. That's all. Right, so moving on to number 26, it says a tuning fork is used to produce a sound wave having a frequency of 512 hertz. What is the wavelength of the sound wave in air at standard temperature pressure, right? So they give you us frequency, which is 512 hertz, right? And we're trying to find the wavelength, or the lambda. So I'm going to go into wherever I have my waves in my reference table, and I'm going to look at whichever one here has wavelength and has frequency in it, right? So the only one that has those two parameters is v is equal to frequency. V is equal to the frequency times the wavelength, right? And I'm just going to fill in whatever they give me, right? So they gave me my hertz, my frequency is 512 hertz, and I still don't, and I'm trying to solve for this wavelength. And you may be wondering, oh no, I don't have enough information to solve this problem. Well, don't worry, you do, right? Because it says this is a sound wave and it's at standard temperature pressure. And if we look over here, we know the velocity of that, right? Because we're talking about the speed of sound in air at standard temperature and pressure, right? And that's going to be 3.31 times 10 to the power of 2 meters per second, right? So that's 3.31 times 10 squared meters per second. That's going to be our velocity of that sound wave. That's the velocity of all sound waves at STP, and this is equal to 512 hertz times our lambda, right? And from here we can divide both sides by 512, and we're gonna get 0. And once we do that, right, we're gonna get 0.646 meters as our lambda. Right, so now we're moving on to number 27. It says, an amplified sound wave produced by an opera singer shatters a glass. Which phenomenon best explains this event, right? So it's going to be resonance. I'm going to give you a rough explanation of what resonance is, right? So let's just say we have a glass. We have a wine glass right here, right? Every single material on this planet has something called a natural frequency or a resonance frequency, right? And what this means is that each material is susceptible to a specific type of frequency, and whenever that frequency is absorbed by that material, it's going to take the characteristic of that wave or of that frequency, right? So let's think of an earthquake, right? We have this tall building right here, and during an earthquake, right, the ground is shaking, right, but it's oscillating, right? It's moving back and forth. So think of a longitudinal wave, right? It's moving forward, then there's a X amount of time, then it's moving forward, X amount of time, moving forward, X amount of time, moving forward. It's in a wave pattern, right? And if this frequency, right, matches the natural resonance frequency of this building is going to start moving left to right, right, or right to left, at that same frequency in that same pattern, right? This is going to start moving left and then it's going to stop moving. It's going to start moving left, and it's going to stop moving. It's going to start moving left, and it's going to stop moving, right? So there's a certain and a specific frequency that every object is susceptible to, and when you play that frequency, or when you play that specific wave, right, it's going to take that wave and it's going to start moving along with it. So just how the building met its resonance frequency and started moving alongside it, right? It started moving, side to side, side to side at the same frequency, at the same wavelength as that wave. The same thing is going to happen here with that glass, right? So let's just say this lady is this opera singer is singing, right? She's emitting these sound waves, and these sound waves are gonna be the same as the natural or the resonance frequency of the glass, and that's going to cause the glass to kind of, if we look at it from a bird's eye view, right, that's going to cause the glass to like kind of oscillate back and forth, right, at the same pattern as she's singing, right? So here it's normal, right? Then it's compressed because it takes in the wavelength, right? So it's compressed, normal, compressed, normal, compressed, and after a while, right, this glass is going to get so thin that it's just going to snap, right, and it's going to shatter because it got too thin and it tried to fold in on itself, which it can't, right? So whatever I'm saying doesn't matter, right? Just know that the phenomenon where something's going to start moving based on a wave, or a wave starts to move something, is usually going to be because of the phenomenon of resonance. Number 28 says the diagram below represents a wave traveling in a rope in the direction indicated. Which arrow represents the motion of the particle at point P of the instance shown? Remember that motions of particles on waves can only go up and down. Motions of particles on transverse waves, at least, can only go up and down, right? So 1 and 3 are wrong. And if you want to know this, there's a cool trick, right? So first of all, they're always going to tell you the velocity, right? So we know that our wave is going from left to right. So I'm going to draw an arrow opposite that direction, right? So now I'm drawing an arrow that goes from right to left, and I'm going to look at this graph from right to left, right? So as I look at it from right, I'm going to look at it before the point P, right? So if I look at it from right to left, right, I'm starting at the right point, and I'm just tracing it. And then notice that as I go from right to left, this wave is pointing upwards, right? And because this wave is pointing upwards, the particle is then going to have to go upwards in this exact instance after as the wave moves forward, right? So the trick here is to switch, is to first note the direction, right? And then look at the wave at the opposite to the direction that it's coming at you, right? Or opposite to the way that it's actually going, right? And you look both before and you look after, and the path, right? If the path is going up, then the wave is going, then the particle is going to go up. If the path is going down, then the particle is going to have to go down. That's all. Number 29 says, if several resistors are connected in series in an electrical circuit, the potential difference across each resistor is what? Right, so there's some key things here, right? It's several resistors, so it's multiple, and we're saying that they're connected in series, right? So I'm going to look here, I'm going to look at my reference table, and I'm going to look all the way, I'm going to scroll all the way back down to energy, right? And specifically electricity, I'm going to look back to where it's a series circuit, right? Because they're connected in a series circuit. I'm going to notice that I is equal to I, right? So I know that my current is constant. And I'm going to look here, I'm going to notice that my voltage is not constant, right? So voltage right? And since I'm dealing with resistance, I'm also just going to quickly write down my resistance formula, R equals V over I. Right? So, if they're connected in series, right, the potential difference or voltage across each resistor does what, right? So here, I have R equals V over I. I'm going to put this in terms of V, right? So I know that V is equal to R times I, right? If I multiply both sides by I, the I cancels out. I'm left with R. I'm left with V alone, right? V is my potential difference, and I know that V is going to equal to my resistance times my I, right? Or times my current, right? But I know that my current is constant because it's a series circuit, right? So constant. So if I want my potential difference to increase, I'm going to have to increase my resistance, right? So that means that it's going to have to vary directly with the resistance of each resistor. If we look here, the total resistance is equal to resistance 1 plus resistance 2 plus resistance 3. So if I want my R to be greater, I'm going to have more resistors, right? And what that means is that my voltage is going to vary directly, right? So the higher my voltage, the higher the amount of resistance, right? The higher the resistance, the higher my voltage, right? That's a direct relationship between the two.